today's lesson we are talking about seismograms. And remember in the last lesson we talked about a seismograph. It was that machine that measured and recorded the earthquake. And it was a pen drawing on a piece of paper. Well, that piece of paper is called the seismogram. So a seismogram is the recording of the seismograph. It's the piece of paper. The seismogram shows two important things about the earthquake. It's going to show the amplitude and the time lag of the earthquake. The amplitude is pretty simple. It's just the height, difference from the zero line, of the recorded waves. We'll show you this with the seismogram. So the amplitude is basically the size of the recorded waves. The time lag is a little bit harder. It involves subtraction. Time lag is the difference between the arrival time of the P wave and the arrival time of the S wave. So what you're going to do is you're going to subtract the arrival time of the S wave minus the arrival time of the P wave. So let's look at some seismograms. The first seismogram was from the large earthquake in 1985 in Mexico City. Again, we talked about this one a little bit. The actual epicenter wasn't even close to Mexico City, but Mexico City was destroyed. It was an 8.1 magnitude, so a very large earthquake. So we see the seismogram here. Think of this again not as a flat sheet of paper, but this used to be a roll. Remember, it used to be a cylinder of paper. And let me get a pen out here. This was a roll of paper. You start reading a seismogram like you would a book. Start in the upper left, okay, and this one happens to start here. So start in the upper left and you follow along. Straight line means nothing was happening. Remember, the pen was just drawing on the piece of paper. Straight line, nothing's happening. These little ticks here, sometimes you'll see these on seismograms. That is for a time. And maybe it's 10 seconds, maybe it's a minute. It kind of depends on how it's calibrated. But that's just basically a time. Let's say it's 10 seconds in this case. So we're going along, going along, going along. Did something happen here? No. This part comes along to here. So what you're doing is you're reading this like a book, trying to find something happening. And right here, so straight, right there. That is the first place that something happens. What is the first thing that happens? Remember, it's the P wave, because the P waves were fastest. So there's the arrival of the P wave. So the P wave happens, it gets bigger, and then you notice that it dies down. Okay, it gets smaller again. Well, the next time something happens is right there. What is the next thing that's going to happen? It's going to be the S wave. So that's the arrival time of the S wave. So there's the S wave. And you watch it, and it's going to get bigger, and then it's going to start to die down. What's the next thing that happens? And this is hard to tell, and when you guys are doing this, it's going to be hard for you to tell too. Maybe I'm going to say somewhere right in here, maybe, is where the next wave starts. That is the arrival of the surface waves. Like I said, it's not always easy to find these things. You're just going to need practice. So P wave arrival, S wave arrival, and then we have surface waves. Now we said we kind of find two things from looking at a seismogram. We find the amplitude and the time lag. Amplitude is the height of the waves. So here to the middle point here. So that's the amplitude. Normally we'll have a scale to measure it with. And we'll look at it the next one. I just wanted to show you on this one. So the amplitude is how high the waves are. And it could be going this way too, so it could be kind of the height this way. Whichever one's biggest, and it looks like the top one is biggest. So that was the amplitude. The second thing the seismogram shows us is the time lag. Remember, that's the time difference from the arrival of the P wave, which was here, and the arrival of the S wave, which was here. So if you can't find the surface waves, don't worry about it. You don't need them, for this part at least. You're only looking at the P waves and the S waves. So basically, it's kind of this from here to here, and that's maybe, I don't know how many. Let's say if these are 10 seconds, 10, 20, 30, maybe 40 seconds for your time lag. The ones I'm going to give you are going to have a scale to make it a little bit easy. For example, let's look at this one. This was from the Loma Prieta earthquake. This was the 1989 San Francisco earthquake, the World Series earthquake. It was recorded in Finland. So earthquake in California, recorded in Finland. Again, first thing, let's look at the amplitude first. Find the highest point, so the highest wave goes straight over there. Find the lowest point, go straight over there. And now pick the biggest one. So it looks like these go by 25, so this one would be 260 about. This one would be 260 about. So it looks like they're the same. So in this case, it would be 260 microns. Micron is like that. So 260 microns is my amplitude. Then we need to find the time lag. The reason we're finding amplitude and time lag is so eventually we can find the magnitude and the epicenter of the earthquake. That's kind of what we're working towards, and we're going to do a lab with that once you've had some practice finding amplitudes and time lags. The earthquake kind of starts here. Again, we have our straight line. The first time anything happens, that's the P wave. You see it's already marked. Gets big, and it gets small. The next time something happens is the S wave. Well, here, it gets big again, so that's the S wave arrival. Get big, and get small. The next thing that happens is the surface wave arrival. So right here, it gets big, and then we're all done. So there are P waves, S waves, and surface waves. The time lag just go down or up, either way, the scale. So the arrival of P wave, go down, right about there. S wave arrival, go down, oops, right about there. So we find this difference. This is in seconds, it says. So we're at about, what, let's say almost 6 seconds here. To 10, to, let's say, if we say 12 seconds, just to kind of be rounding. So now do 12 minus 6. So our time lag is going to be about 6 seconds. So our 6 seconds for our time lag. So that's what you're going to be looking at. You're going to be finding the amplitude and finding the time lag from the seismograms. Let's look at some more. These are from the Northridge earthquake. That was the last major earthquake in Los Angeles, 1994. Hopefully it's going to open here. So again, these are recordings from the earthquake that happened in Los Angeles, but it's going to be recorded in lots of different cities. There we go, finally. So this one, Northridge earthquake, recorded at CMB, an ANMO. I don't know what that is. So we look at it again. First thing we're looking for is the time lag, or for the amplitude. Let me see if I can get my pen. Doesn't look like I'll be able to get my pen. That's okay. So take the highest point, go over. Take the lowest point, go over. Which one's bigger? It's definitely going to be this one. So this is in millimeters, so it looks like probably like 4.1 or 4.2 millimeters for my amplitude. So that's all you do to find amplitude. Find the highest point, go over, lowest point, go over, and take the biggest one. So my amplitude is about 4.1 millimeters. Now we have to find the time lag. So again, start at the beginning, go over until something happens right here. I wish I could get a pen. Can I get a pen anyway in this? Maybe not. Okay, I can at least mark it there. So the first thing that happens is going to be the P wave right there. It gets big, and it gets a little bit smaller. So the next thing that happens is the S wave. So probably right about there somewhere maybe. Then it'll get big and get smaller again. We'll have the surface wave. Kind of hard to tell where it is. But again, we don't need the surface wave to find the time lag. So if we say it was here for the P wave and here for the S wave, go down to your time scale, go down to your time scale, and we are not very many seconds. This is 2 seconds here, so this would be 1 second. So we're at about maybe little over, I don't know, maybe a little over half a second or something like that for a time lag. This one, again, same earthquake recorded in a different place, gonna be a little bit different. We see again, we look at our time lag or our amplitude, go over, we're at about 1.25 here. Go over here, again about 1.25, so it'll be 1.25 millimeters. Start at 0 until something happens. Oop, right there, so there's your P wave arrival. Keep going until the next thing happens. Oop, there's your S wave arrival. So you get your time lag is about 3/4 of a second, or 1.5 seconds. And then this one's at about 2.25, so you subtract those about 3/4 or so a second. Why do you think this one had a bigger amplitude than this one? Probably because it was closer. The closer it is, the more violent the shaking. Also, you think, well, does time lag work that same way? Yes. The closer the P and S waves, the closer you were to the epicenter. We talked about that earlier. We looked at it in class. Time lag basically tells you distance. Because the P wave is traveling faster than the S wave gets further and further behind the P wave the farther they are from the epicenter. Think of it like a race. Let's say you're racing against an Olympic sprinter, and you're both at the blocks, the gun fires, and you both dart off. After the first, let's say 10 meters, the Olympic sprinter is going to be ahead of you. But he's not ahead of you by very much. There's going to be a small difference. Well, let's say now you're going 100 meters. In 100 meters, that Olympic sprinter is going to be way far ahead of you. That's this. Okay, the P wave is the Olympic sprinter. The P wave rushes off. The S wave is traveling far behind. So this is how you're going to tell distance. How big the time lag will tell you how far away the earthquake was. Okay, let's go on to the next one. These were the answers. So we have to see the answers. Hard to put them on the same page, though. We had our P wave and our S wave. We have our surface waves. Look at this one. I think I have this one where I can draw on it. So let me get out of this. And I think I have this on the next one. So we can draw it. Yes, so I put this one on here so we can actually draw on it. Okay, so again, first thing, find your amplitude. Take the highest point, go over there. Take the lowest point, go over right about there, probably lower. This one looks like it's about 130 microns. Microns are smaller than a millimeter. This one, it looks like it's 160, probably, microns. So the amplitude is the bigger one. 160 microns is our amplitude. I always take the bigger one. Now we need to find the time lag. So again, start at 0, go over till something happens, up right there. So that's going to be my P wave arrival. Gets big, now it gets small. So keep going until it gets big again, right there. There's going to be my S wave arrival. Gets big, now you're waiting for it to get small, and then big again, it looks like right here. So then the surface waves are going to start here. And again, if you have problem finding the surface waves, you don't need to worry about it, because you don't need the surface waves to find the time lag. You only need the P and S waves. So we go down, we take our P wave, go down, take our S wave, go down, and now we subtract. So this is about 7.5, so 7.5 minus, let's say 4, let's just say 4 to make it easy. So that would be about 3.5, and it's seconds in this case, so 3.5 seconds would be my time lag. So that's all you're going to do. Now the next thing we're going to do is we're going to show how this will let you find the epicenter. So, and to do this, I'm starting off with just a math problem as kind of a simple answer. So I said, let's say that my grandpa and my sister leave my uncle's house to come to Dallas. They leave at the same time but are in different cars. Grandpa always drives 40 miles per hour. So he's not stopping for stop signs, he's just going at 40 miles per hour. Same thing for sister. Sister always drives 70 miles per hour. Not stopping for stop signs, slowing down for turns, anything, always going 70. Which one of these is analogous to the P wave? Her. Okay, so she's the P wave. Remember, the P waves are almost twice as fast as the S waves. So that's why I picked those numbers. So the P wave there is about twice as fast as the S wave. Okay, so they both leave my uncle's house and they're coming to Dallas. My sister arrived in Dallas 3 hours before my grandpa. How far is it to my uncle's house? Well, do we have enough information? We do. We do have enough information to solve the problem. If I go back again to the last slide, we had our information here, and we said that our sister was our P wave. She traveled really fast. The grandpa was the S wave. He was a lot slower. And then the 3 hour was the difference. So that 3 hours, that was our time lag. So we have enough information to figure out how far it is to my uncle's house. We know the formula for distance. Formula for distance is rate times time. Since they both traveled the same distance, we just set them equal to each other. Sister's rate times time equals grandpa's rate times time. And now what we do is we just fill in what we know. We don't know how many hours it took either of them. So we're going to let sister's time be the variable, t. Grandpa took 3 hours longer, so grandpa becomes t plus 3. So we just put it in there. So sister was 70t equals grandpa's 40 and then t plus 3. Use the distributive property, 70t equals 40t plus 120. Combine like terms, 30t equals 120. Solve for t, so you divide both sides by 30, and we get 4 hours. So we know his house was, so we know the time was 4 hours. So the distance, we just go back to our rate times time. 70 times 4 is 280 miles away. So we know that my uncle's house was 280 miles away from Dallas. So do we know exactly where its house is? No. We just know that it's 280 miles from Dallas. So is it inside the circle, outside the circle, or on the circle? The circle has a radius of 280 miles. So the answer is, it is somewhere on the circle. The radius of the circle is 280 miles, so we know that his house is somewhere on the circle. So basically there's an infinite number of possible locations for his house at that distance from Dallas. So if next week they went to Austin instead of Dallas, would that help locate the house? Definitely, because then we could draw a circle from Dallas. So let's say that we found that from Austin, it's 200 miles. So now we know it's somewhere on this circle. These circles cross in 2 places. So we know that my uncle either lives there or there. There are only 2 possible locations for my uncle to live. We don't know which one it is, but there's only 2 places at the correct distance from both cities. So what should we do next time? Well, next time we should, let's say they go from a different city. Or they're going to, let's say they're going to, I don't know what, El Paso, somewhere over here. So when I draw a line from El Paso, and I draw my circle, and let's say it goes through like that. Well, then we know my uncle's house is right there. This is what we do to find the center of an earthquake, or find the epicenter of an earthquake. This is called triangulation because you need at least 3 seismograms to find the earthquake. So like I said, This is basically just exactly what we do to find the position of the epicenter. We look at 3 seismograms and we find the time lag. Okay, it was 1.5 minutes. That means it was 900 kilometers away. We draw our circle with the distance, with a radius of 900 kilometers from that station. Then we find the next one, and it was 1,800 kilometers for a time lag. So we draw a circle with a radius of 1,800 kilometers. Then we do our third one. We find that this circle is going to have a radius of 3,300 kilometers. So we draw that one. And what we're going to find, hopefully, is that all of our circles intersect in one place. That place is the only place on Earth that is the correct distance from all 3 of those stations. So again, the key is the distance. It's not just the circles. The circles are representing distances. If you only have one recording, there's an infinite number of possible places on that circle at the correct distance away. If you have 2 stations, there are 2 possible locations, the correct distance of these 2, the correct distance from those 2 stations. Once you get 3 stations, then there is only one place on Earth that's the correct distance from all 3 stations. So that's how you're going to find the epicenter to some earthquakes. So we're going to do a lab on that. I'm going to give you the seismograms. You'll have to find the amplitude, you have to find the time lag, you'll find the distance, you'll draw your circles with a compass, and you'll hopefully find all 3 of the distances match in one point. This is again showing the same kind of thing. This earthquake, or this is one earthquake, recorded in lots of different cities. How do you know which city is the closest? You look to see which one has the shortest time lag. So Tokyo was the closest city. Sydney the next closest because the next biggest, or the next smallest time lag. So that's what you're looking for. So what you could do is you could just start drawing circles from these cities with the distance of the time lags. And you would be able, or hopefully all these circles would then cross at a location. And that would be the epicenter of your earthquake. And you're going to be doing that in lab.